Yeah, hello Shika. So I think this will be the last live session for this NPTL course. I'm not very sure because as you have seen in the website, it's the last entry for the live session, but it might get extended up to two also, up to 2 week also. So so your gate exam date are out, right? Okay, so I hope you are up with your preparation now. Okay. Oh, okay. Wait a minute. Huh? I am. Yeah.
And there is one problem.
Wait. So eco problem. Yeah. Now you can speak.
Ma'am, actually, phase one classes were for whole week, and they are not provided recording link for
Oh,
Tuesday, Wednesday, Thursday. Actually, I want to revise those now, but even I mail them also, but they are saying soon. But gate exam is coming.
so you are talking about the phase one, the live session classes, right?
Yes, ma'am. Monday and Friday, Sunday. Those links are provided, but in between are not there.
Okay. So I will convey this to them. So
Okay, ma'am. Even I emailed them, but they are saying that they will soon upload. But I think time is getting over now.
so let me check. In the gate portal, you have the live session link.
Yes, ma'am. It is like live mentoring sessions, phase one and phase two.
Okay, chemistry. Yeah, there's a recording link for Monday, Friday, Sunday. Yes, for Saturday, Friday, Thursday, Wednesday. Okay, I will
But
pers.
your classes links are there.
Yes. So I will personally message them and I will request them to upload as soon as possible.
Yes, ma'am. It will be beneficial.
Mm-hmm. Because I think all, if they have already recorded it, if they have not, then it's a problem. But otherwise, if they have recorded it, then they might have uploaded, because this phase was ended at the end of November, and or I think in between of mid of November, so they might have all the recording till now. So I will request them to upload it. Okay.
Okay, ma'am.
So yeah, it's already 6:06, so I think I should start the class. So a little introduction. I am Anjali Negi. I am a currently PhD student in IIT Kanpur. So in today's live session, so let me just share my screen. And Shika, if you don't see my screen, then mention it, okay?
Okay, ma'am.
So are you able to see the screen?
Yes, ma'am.
Okay. Yes, so the first problem is I have taken is from GATE 2014, question number 26. So this problem state that we have expression for psi, that is the wave function, is a proposed hydrogenic wave function where z is the atomic number, r is the radial distance from the nucleus, and theta here is the azimuthal angle, and is a constant. So n is a constant carrying some it's not the Avogadro constant, but sum of some constant value. Okay, and the incorrect statement about the wave function psi is. So we are given with 4 options and we have to find out the incorrect statement. So before that, let's move into some basic. Yeah. So talking about hydrogenic wave function, and that is 2 in a spherical coordinate. Okay, so when we talk about the hydrogenic wave function, so the Schrodinger equation, start from the Schrodinger equation for the hydrogen atom, which we can actually write as the Hamiltonian, and the wave function is equal to energy E multiplied with psi, that is the wave function again. Here you must notice and observe that the wave function and the Hamiltonian are actually the function of small r, theta and phi. Okay, here also small r, theta and phi. So this is when you convert your Cartesian coordinate into the spherical coordinate, and I am not going into the detail of the derivation, but let's keep that in mind that while going from Cartesian to spherical coordinate, we have x equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. And also, if you expand this whole expression, like your Hamiltonian is equal to the kinetic energy plus potential energy, where your potential energy is in the Coulombic expression form. Okay, and when you open your Hamiltonian and expand the given expression, you will find that you can actually separate the whole equation into 2 parts, that is the radial and the angular part, and you can somehow write the wave function into the product of 2, that is the radial part and the angular part. Here the angular part is the spherical harmonics that is actually denoted as capital Y, and which is the function of theta and phi. And for the radial part, we separate the part containing only small r, that is the distance. Okay, and between the nucleus and the electron, and this capital R is the radial part. Now if I just simply write down this capital R, will give me quantities like n, which is the quantum number, L is the azimuthal quantum number, and for Y it will give me L and M, which is azimuthal quantum number and magnetic quantum number. And from here you can actually find out, because it's a function of theta and phi, you can actually find out theta and phi, and there are predefined, the derivation is there. You can just check out the final expression for theta and for phi as well. Okay, so yes, now coming towards a problem. So there is a mention of some nodes in the given 4 options. So what are nodes? So node where the probability of finding an electron is 0, and for the radial node, a radial node is a sphere rather than angular node. Okay, so radial node is actually a sphere, but when we talk about the angular node, it is a plane, basically flat plane or plane, I can say only that, and that occur when the radial wave function of an atomic orbital is equal to 0 or it changes some sign. So whether it is 0 or it changes the sign, in between that there is a node. Okay, so that is what we call a spherical uh, radial node. So if I just say there is a 2s, so in between here there will be a radial node. For angular node, for example a p orbital, there is a plane passing, like we can say it's a xy plane. That plane will be angular node. Okay, and when I only mention node, then it is, I can say that it is a point. Okay, now the total node expression will be n minus 1, where my n is the quantum number. Okay, and principal quantum number, and my radial node will be, the expression is n minus L minus 1. For angular node, it is simply equal to azimuthal quantum number, that is L. So keeping these thing in mind, so I have also written the expression for calculating magnetic quantum number m. So for calculating magnetic quantum number m, you must have to watch out the expression given to you, that is the wave function that is given to you. So if my wave function has some expression where my e is the exponential having I iota m phi, okay, where my any number there will be equal to m, okay. So now the second thing is the azimuthal quantum number, that is my L. So for L, there are two possibility that we can go through to find out what is the L there. So first of all is the angular part of psi. So since I have mentioned that my psi have one radial and one angular, radial and one spherical part, correct. Now this spherical part have theta and phi expression, that is why it is angular part 2, and this have only the r expression, correct. Now when I am going through angular part only, then I will check out that there is if there is some cos theta or sin theta summation, or only cos theta or maybe only sin theta, doesn't matter, but we just have to check out the power of them. So simply sum their power x plus y, it will give you L. So that will be my angular part. From angular part I can calculate the azimuthal quantum number. Now from radial part, if you go through, so again coming only from radial part, if I calculate the L value, then what will be what will be the steps, that I just have to go with the pre-exponential factor, that is or not exactly that is the factor which is wait so yeah, so that is the expression, that factor that is there from uh, just before the exponential e, okay. So this pre-exponential factor, you just have to find out the minimum value of r. So the minimum power of r, power of r will be L, okay. So this is there. So we have just seen the two different method of calculating L, from radial and from angular part. Now the problem that we have in our hand is the given expression for the psi. So the psi expression that was given to us was nr6, this bracket, and this exponential minus zr upon 3 cos theta. So now if we just simply solve and calculate what is n, L, and the radial node and the angular node. So also, if I have mentioned it here, I don't know. So yeah, so I think I should mention it here, that for n, when there is an expression z r n a naught, n will be, n is here, okay. So simply for n, you see that your expression here is this, where your n is actually 3. Now talking about my L value, so I can calculate whether it from angular part or from radial part. So let's calculate it from angular part. You see that there is only cos theta present there, so cos theta power, that is 1. Or if I just simply calculate it from radial part, then from radial part it is the power of the pre-exponential factor that we see here, and we just go with the minimum power of r, okay. So again it is 1. So from both ways we are getting the same correct value, 1, okay. Now just calculate the radial node. Now calculating the radial node, we have 3 minus L, that is my 1 minus 1. So this will be 1. So there are one radial node, and for angular node, since it is equal to L, I will have only one angular node. Now going again back, to my problem that we have. So the let's just go through. So we have the expression, we calculated that my radial node is equal to 1 and not 2. That is why this is the incorrect statement here. And the angular node is actually 1, which was equal to L is equal to 1. So it's correct. Now my psi is equal to 0. That is, there is a node present in the xy plane. That is also true. Now talking about the D option, the size of the orbital decreases with increase in atomic number, the size. So when this is also true, based on the periodicity, you see that as the atomic orbital size decreases, the atomic number is also increased. Okay, because of the why it is the effective charge is increased, because of the increase in the atomic number. That's why the orbital size decreases. Now this is the correct option for R26. That is, the incorrect statement is B. So any doubt?
Ma'am, please solve the question again. Last part where question was actually solved.
Yeah, this one.
Yes, ma'am. Where we solved the expression, na?
Mm-hmm.
Last part.
Okay, wait. So this one you are talking about?
Yes, ma'am. Ma'am, one slide before. Yes, ma'am.
Okay. So
You were telling here e to the power minus.
yes,
You were
okay.
telling inside na e to the power minus zr n a naught.
Yes. So I was just telling that when we are asked about the principal quantum number n, then at that part you just have to look at the expression of exponential carrying minus zr upon n a naught. Basically here you can't see a naught here, but there is n present here. It's a hydrogenic wave function, not actually the hydrogen wave function. So that's why there is not a naught present there. So n will be 3 here, okay, by just looking at this particular expression. And then talking about my L, so for L we have seen that there are two ways of calculating L. From angular part only, just sum up the power of the cos theta and sin theta. So sin theta is not here, so just the power of cos theta, that is 1, will be equal to L. And for the from the pre-exponential factor 2, I can actually calculate the value of L, that is the minimum power of my R. So that is, if I look into here, the power of my R, the minimum power is 1. So again it's correct from both the ways that we calculate L. Now after we get L value, we can calculate the nodes. So the radial node and the angular node are calculated using this expression n minus L minus 1, and angular node is simply L. Now since my angular node is simply L, it is equal to 1. Radial node, that is 3 minus 1 minus 1, that will be equal to 1. So is it clear now?
Yes, ma'am.
Okay. Okay, just okay, 1 minute. Okay. So moving towards our next problem that we have. So this is again a GATE 2012. I think it is it 2012, 2014. I will correct it later. I think it's 2014 problem. Uh, okay, so this problem is question number 11. So this problem states that the angular part of the wave function for the electron in a hydrogen atom is proportional to. So basically, as I have just told you, that we can write our psi, which is uh, uh, theta, phi, and n dependent, basically into, sorry, r dependent, basically into radial and some spherical part. We can write it in the product of these two, and since this is my spherical harmonics and this is what we call as angular part, yes, so this part is actually given to us. So this will be the proportional part to my spherical harmonics. So we are asked about to calculate, so we are asked to calculate value of L and the value of M. So now let's go back. ठीक है. So the next, yeah, so this is what we are given. So we are given this expression as the angular part of psi wave function, and we want to calculate M and L value. So basically the L value that I have told you, there are two ways, and since we are given only angular part, then we will sum up the power of sine and cos theta. Since the power of sine is 2 and the power of cos theta is 1 here, so it will be 2 plus 1 equal to 3. So my L, that is my azimuthal contour number, is 3. Okay, so we wanted to give L and M value, and now I have only 3. And now for M, so in previous also I have told you that there is an expression for M where you can actually just watch out the expression where E have iota in their power, in its power, with M and phi. Okay, so the any constant value will be equal to M there. So here we have expression E exponential to the power 2 iota phi, and that's why my M will be plus 2. So L comma M was asked, so we have our answer like 3 comma 2. Okay, so any doubt, Shika?
No, ma'am. Okay.
Okay. So this is the correct option number C. Okay. Now this is another problem from GATE 2012 again. This is again I think from 2014. So it's very simple. If you can just simply know the equilibrium expression for the given reaction, you can calculate the dimension of that equilibrium constant. So I think you can solve it. So Shika, just give it a try. So yes,
it will be dimensionless quantity.
Actually no, because just simply write down the equilibrium constant value for this expression. What you will find that the constant for this particular reaction is, Shika, you can mute yourself. Okay, so the thermodynamic equilibrium constant expression will be the concentration of the product upon the concentration of reactants or products. Okay, so now for the given reaction we have concentration of C upon the concentration of A and the concentration of B. So what will happen here, that if I just simply cut out the units, so this will be mole per liter, this will be mole per liter, okay, and we will have unit in mole inverse liter. So this is the correct unit for the equilibrium constant of this particular reaction. Okay, so is it clear to you?
Yes, ma'am.
Okay, so the correct option is option number B. Okay, this is another that I will solve, but I think we should watch one video solution of one problem. Okay. Hello everyone. In this video I will be solving GATE 2013 chemistry question number 44. This question states that among the following octahedral complexes, the one that has the highest enthalpy of hydration is. So we are given with the octahedral complex of calcium 2 plus, manganese 2 plus, vanadium 2 plus, chromium 2 plus ion. Okay, so let's move into some basic. So here, this is actually the application of CFT or CFSE, the crystal field theory or crystal field splitting energy. So the hydration enthalpy is stated as or defined as the heat liberated when 1 mole of a gaseous metal ion is dissolved in water. So we can imagine the dissolution of the metal ion, for example Mn plus. This is a solid or gas, and when it is dissolved in water, so it makes a 6 coordinated complex, which is octahedral complex, and there is a liberation of energy, which is known as the hydration enthalpy or hydration energy. So if you define your M2 plus, for example, so it will be surrounded with a water molecule in a way of octahedral. So a total of 6 H2O molecule will be in its primary shell or first shell or primary shell, and after that it's a vast hydrogen bonded network of water molecule. So it's an infinite dilution, okay, of the metal ion. So the point to be noted here is that that the hydration enthalpy is directly proportional to the effective nuclear charge or the Z effective, and it is inversely proportional to the radii. So while moving from left to right, from scandium to, okay, so it's a positive. Yeah, so from scandium to positive to zinc 2 plus, my Z effective increases, and my radii decreases. Okay, or I can call it as a ionic radii or simply the metal or ligand distance. So here, the experimental hydration enthalpy or hydration energy can be written as the sum of the theoretical hydration enthalpy or the one we calculate plus CFSE of the particular complex that we are talking about. So here you can see that this is a plot for the hydration energy, and this is the first transition series. Let's start from calcium to zinc, and this is manganese. All are in 2 plus ionic state, and so these cation are arranged in this from left to right, and so as predicted by, or theoretically we can say that if we move back, yeah, so the Z effective is increased and radii is decreased. Hence, the hydration enthalpy should gradually increase overall from moving uh, left to right. Okay, in the first transition series. So when we are moving from left to right, my hydration energy or enthalpy should increase gradually. Correct. But what happens experimentally that we see that only calcium, manganese, and my zinc lie at exactly at the predicted or theoretical hydration energy, this dashed line. But other, for example, let me say vanadium, okay, 2 plus, this actually lie uh, above the theoretically predicted hydration enthalpy value, and hence it has a value which is uh, greater than the theoretical hydration enthalpy. Uh, so we say that there is a role of CFSE here, and you can also calculate that the calcium, manganese, and the zinc, which are actually lying at the theoretical line, dash line, is having a CFSC equal to 0. But other metal or transition metals which don't have CFSC equal to 0 will be lying above the predicted or theoretically calculated hydration enthalpy value. Hence, you will see a trend uh, something like this. Okay, so this will be the trend for the experimental hydration enthalpy observed. So let's calculate. So here I am just writing down the ions that we have in our problem. That is my calcium 2 plus, my manganese 2 plus, vanadium 2 plus, and my chromium 2 plus metal ion. So for these, you can write the electronic configuration. Either you can write it in full, that is my argon 3d0, argon 3d5, argon 3d3, argon 3d4. So remember, this is a octahedral complex and it is a high spin. So my CFSE that you will calculate will be, so as you can write it here for calcium, T2G0, EG0, this will be equal to 0 overall. For manganese, it will be, as it is 3d5 and high spin, it will be T2G3, EG2. In T2G, you remember that there is a stabilization of minus 0.4, and in EG, there is a destabilization of 0.6. So it will be 3 into minus 0.4 and then plus 2 into 0.6. So overall it will be equal to 0. So in vanadium it will be T2G3 EG0 equal to minus 1.2 delta naught. And for chromium it will be T2G3 EG1 equal to minus 0.6 delta naught. So remember that we take CFSE magnitude. So hence the highest CFSE that we have is for vanadium 2 plus ion, that is 1.2 delta naught. So here in our problem, among we were asked among the following octahedral complexes, the one having the highest enthalpy of hydration is. So we know the trend that while moving from left to right, it should be uh, so it should be from first calcium and then vanadium and then manganese and then it should be uh, first chromium and then manganese if I follow the Z effective trend. Okay, but we know that the experimental hydration enthalpy is actually equal to the theoretical hydration enthalpy plus CFSE. So plays a major role here for the to determining the actual hydration energy or enthalpy value. So the highest in the CFSE that we saw in our plot also was for vanadium case. Yes, so in our given metal complexes, my vanadium H2O6, that is the octahedral complex, gives me the highest hydration enthalpy value. Okay, so I will recommend you to go through the NPTEL reference, Application of CFT by Professor Debashish Ray, Department of Chemistry, IIT Bombay. Here is the link below. Thank you. So if you have any doubt, you can ask. Otherwise, I will move to the next problem. Okay, so this is from GATE 2014. So this problem state that suppose we have psi1 and psi2 and these are the two hybrid orbitals, and we just have to calculate the angle between these two given psi. Okay, so at one glance, if you look into the hybrid orbital, you will look that this is 3s and this is 3px 3py. So my first intuition will be that this is a sp2 hybridized orbital, but if you go by that intuition, you will find that you will predict that the angle of the these two hybrid orbital will be 120 degree, which is not the case. So the actual case is that you can go through um, by simply calculating it like a dot product. You calculate between the two given vectors. So if you just do the calculation on based on the dot product expression and calculate the angle between these two vectors that are basically psi, you will find out the correct option. Now what I will do, yeah, I have this, so let's start from here. Yeah, so since I have been given psi1 and psi2, there are two different expression here. So for psi1, let's just remove it. So this dot product will give me cos theta. Now this cos theta is simply the dot product between these two, psi So if you do the calculation, what I have found out that this is basically around minus 0.97, which I can just simply put minus 1. And for that expression, you know that theta at theta is equal to 180 degree, my cos value is minus 1. So and my theta is actually 180 degree. Okay, now so the given range for this numerical problem was from 175 to 185, and so you can simply give your answer as 180 degrees. So any doubt? Okay, so I hope it's clear. Question number 11. So this is another quantum mechanics problem, small based on the postulate.
Hello everyone. In this video, I will be solving GATE 2015 chemistry question number 11. So this question states that which one of the following plots represent an acceptable wave function. So we are given with 4 different wave function A, B, C, D. So before moving into the correct option, let's discuss some basic. So for the acceptable wave function, we have following conditions to be satisfied by the wave function for the particular system or particle. So the function must be a single value function. And the second point is that the function should, when I'm talking about the function, I'm talking about the wave function psi xt, okay? And the function should be normalized. For normalized, it means that the conjugate psi psi of psi is psi star multiplied with psi should be equal to 1 from minus infinity to infinity, correct? That is, it must have a finite value, and by finite value I mean that for every single value of x, by psi xt should have a single value at particular x, okay? And again, it must be continuous in the given interval. For this, you will see that my wave function should have or should be continuous in the given particular interval for it to be the acceptable wave function. The fourth point is that the first derivative must be continuous on the indicated interval. So that when we are talking about the derivative, so derivative of any function is equal to gives me mathematically the tangent at a particular x. So for any given, I will discuss it in the next slide also. So for any given wave function, so at any particular value of x, so there should be only one direction or the tangent. So such that the first derivative must be continuous. Okay. So the last one is a boundary condition must be satisfied by the wave function. For our boundary condition, when you will be discussing or studying the case of, like, for example, a particle in a 1D box, you will see that there are set of boundary condition that my particle follows or my wave function follows is such that that at the boundary my wave function is equal to 0. Okay, so those are some boundary condition. So these are the point for my acceptable wave function. So here, uh, so all the four options that we are given with, the if I apply the condition, so at for A you will see that this is not a continuous wave function. Okay, so this is not continuous. For my wave function should be continuous, there is also the physical meaning, because for this particular region where my wave function has no value, or you can say that it has disconnectivity, so at that point the my particle probability finding of the finding the probability of finding my particle is 0 there. Okay. And for B option, you can see that this is not a single valued function for a particular value of x. So at any value of x, for example here, you will see that we have a different value of psi xt, which is not the condition that we want for our acceptable wave function. Okay. And for C, you will see that this is a continuous wave function, but here the first derivative is not continuous, because at any peak point or any sharp point, you will see that we have the derivative of this function is not continuous. So here we have different direction of our tangents, and therefore this wave function is also not acceptable. For D, you will see that the wave function follow all the condition, and hence it is the acceptable wave function among the all different options we are given with. Okay, so this is a correct option. And here I am attaching the NPTEL reference for lecture number 4, postulates part 1, by Professor K.S. Sebastian, Department of Chemistry, IISc, Bangalore. Here is the link below. Thank you.
So, any doubt, Shika?
No, ma'am.
Okay. So, that's all for today's session. So, if you have any further doubts, I think I have shared my email ID to you also. So, you have my email ID?
Yes, ma'am.
Yeah, so yes, actually, the recording links are available in the Gate portal itself. So if you go to Google and search for Gate NPTEL or Gate portal, then you will be directed to a site of NPTEL Gate where you can search for. Actually, I can just show you. Right. So if you simply go to Gate portal. So here you can go with phase 1 or phase 2. Phase 2 is the one which is going on. Phase 1 is completed. So you can go here, search for chemistry. So basically for Tuesday, Wednesday, Thursday and Friday, and Saturday. So many of the links are still not available, which I will convey them today. So for other, you can just click here, and then you will find the director to the YouTube channel of them where the video is already uploaded. So here you can check it out. Otherwise the video solution are also there, so you can just simply go to the video solution and then go to the chemistry, then select either topic wise or year wise. Okay, and you have by sequence you have a video solution of each problem. So for phase 2, so there are only two live sessions are going on. One is the one that we had today, the other one is on Thursday. So these video link will be, I think, available to you when the phase 2 is completed. Otherwise I will actually prefer you, I think, I don't know how other mentors are doing, but I am already uploading my videos to in my YouTube channel, the live videos. So you can actually subscribe to their video YouTube channel where they are uploading their videos, so that if there is a gap between this portal and their YouTube channel video uploading, then you can directly get the video from there, but if it's not uploaded here. So I hope it's clear to you. So okay, so that's all for today's session. Thank you for joining.
Okay, thank you, ma'am.
Yeah, thank you. If you have any doubt, Shika, you can mail me, or if you have any other request, you can also mail me. Okay.
Yes, ma'am.
Okay, thank you so much.